So we're happy to have Ryo Yamagishi here. We're speaking about duality involution on symplectic moduli spaces.
Thank you for introduction. Thank you for invitation. So, next, I'd like to talk about the symplectic moduli and also the operation of the moduli that I call the duality involution. So, basically, the motivation of this topic is to construct a new example of a compact symplectic variety. Okay, the job work with Shunyon in National Taiwan University. So,
Which university?
National Taiwan University. Let's start with a surface. Up to the polarization. So, the philosophy will only of the surface that is either Imperial surface or Argentine surface. This is very depend over the complex ownership. The main object is the view. The object is C for fixed numerical invariance rank from Chan countries. So this is the C with respect to the fixed polarization. Leadership numerical invariance. So, as you know, this is the objective variety with the no, in general. So if the gives cutting stability is equivalent to the stability, then this model will become smooth. But in general, there exists circulating temperature sheaf, and in this case, the model is singular. Actually, in this topic, we will focus on the singular model.
It depends on these parameters, right? Whether it's singular or not, right?
This depends on the parameter. We should so if we get this numerical intent at the homology class, and if it is not primitive, then we expect to come singular.
Right, exactly. And
they are co-prime.
And you're using some kind of a generic polarization.
So if we need to choose a generic stability function,
The polarization, you call it a stability condition. Oh, H. I see. And H is what? Sorry, what
just a polarization output device.
H is a polarization. Yeah. Do you mind using putting this on? Thank you.
The boundaries are C1 and C2. What are those?
So these are the origin, the random machine, and C1, C2 are chamberses, first chamber and chambers.
Oh, does that? Sorry, it doesn't have a strap.
Oh.
Okay, there we go. Good, perfect. Great. Okay, wonderful.
In the next main object is duality involution. In order to introduce this operation in the module space, the program we assume that the first chapter is linear and also the main stable part of the module space is going to be this thing or so there are two notions of stability of a shield. So one is the give the stability and there is also a notion which is called stroke stability or mu stability. So this is mu stability stronger than the cubical stability. So here we assume that this is not, so this is for the cubical subject of the module space and then for so under this assumption we can take the position. So this is just given by taking the dual over shift. So the picture. Justify rational it is not defined table we have on the machine system. So this involution has the following properties. The table part. The common so in here, taking the zero shift without the new stability. So this is when you find one. If you regular on this part, but in general, you do have stability not without undertaking if you have. But here it is only regular on this.
You say stability is preserved in this case, not just on the
Preserved on this part. New
This part.
preserved.
on that part.
Under the taking new, but give the custom stability not preserved in general.
That one's not preserved.
So for this reason, this is just by rational. Not to bring it down in the holes.
So sorry, this mu stable. What's
New
mu then? That's not the H. Then. So what's mu?
stable also with respect to the chosen polarization. So in general, give the color stability implies give the color stability aspect. With the implications of the stability. in particular, physical stability, new stability, slope stability, so physical stability.
Physical stability is weaker than slope stability, you say.
And also the different physical stability.
Ah,
And also actually different they have different implications.
oh, I see. I see. So we want to think about we want to think about this mu stability as being as like a more generic stability condition than the G then, say.
Yeah, actually, this is stronger than physical stability. What do you mean by more general?
Like if you have two, if they were just looking at stability conditions, when you make a stability condition more general, if you perturb it, then the stability condition is stronger to be stable. But not
Oh, yeah,
semi-stable.
yeah, this is more general. For more general shape, this is fine.
Like if we were doing stability conditions, just a single stability condition theta, so like a character, then if we perturb the character, then the stability condition is a stronger condition for the perturbed one. So we should think about it as similar to that, the relationship
Yeah.
here.
I would say that.
No,
Then, I think you were considering the change of polarization rather than the change of to notion of separate condition.
oh, sorry, I mean, G would be the perturbed version of mu. It's like if you have the zero stability condition and a general stability condition theta, then zero stable, that implies theta stable, which implies theta semi-stable, which implies zero semi-stable. That's a similar relationship, right?
Oh, yeah, it's not.
But it's not the same type of thing. G isn't obtained by somehow perturbing the omega or something.
So this kind of this function around the same space. Yeah.
But that's the same as what I'm saying. Like if you take like representations of a quiver, right, a quiver variety, the zero stability condition versus a general stability condition theta, you get the same relationship, right? And it's on the same space. So, but we shouldn't think about it as similar to that. To the two different types of stability condition or something like this.
Yeah, the relation. I think,
Maybe at some point you'll give us a definition of the Giesecke stability, but I guess if we don't need it.
I think that the definition for the Gilbert stability, we consider the reduced Hilbert polynomial for
Oh, you have the inequality on the Hilbert polynomial. So it's more information than just the rank
Yeah. So
and degree.
the Gilbert stability involves the second chapter, but the Mills stability
Only involves the first
about
one.
the first.
Right, yeah. So it's like a fine, I would think of it as being like finer. If you have a stability condition with like on a space of characters that's like three-dimensional, then if you set C2 to be zero, then you're looking on a smaller space, and then you perturb into the C2 direction, right?
Yeah.
I think it's similar. Okay. All right. And but the point is that this works for mu stable, but not for Giesecke stable, is what you're saying. Even when C1 is zero. Okay. All right. But because the mu stable only uses the C1 anyway, and not the C2, then when if C1 is zero, then I see, but these subsheets could have C1 not equal to zero. All right. You're not following this discussion. It's just yeah, I'm trying to understand what these stability conditions mean. But yeah, I think that you can all just, if you don't know what We could define it, Rio tried to define it, but basically, the stability condition is like, these Fi parameters, you turn on a parameter, you get an open subset before you take the quotient. And there's two different ways of doing it here. One which only uses the first Chern class, and one which takes into account the first and the second Chern class. So if we need more explanation, just ask.
How does this reflect on the equations? The term classes.
How does this reflect? Well, so I think it's just you can explain, but he has this condition that you have these sheaves, and you want to say that for every subsheaf, this first or second Chern class has an inequality that's satisfied with for the subsheaf with respect to the larger one. So for slope, it's just you take the degree divided by the rank, and that cannot get bigger. And the degree is basically more or less the first Chern class. But now with Gieseker stability, you use the whole Hilbert polynomial, which is some function of both the first and the second Chern class, and you again get some inequality which replaces this slope. But I don't know exactly how to express this inequality in terms of C1 and C2.
Just
So when you say polynomials are this whole,
other polynomials, we can evaluate using by looking at the correlations.
so one by one, every coefficient is smaller.
Yeah.
Yeah,
exactly.
Like, yeah, if you have the same slope, after like you can like remove the ambiguity by looking at the C2. So like you first compare the C2 point charge, and after you look at the D0. So,
Anyway, if we need to know more, we can ask again.
So next we explain the motivation for this.
So you're talking about the how states of brains.
yes, like R is the D4 point charge, like C1 is the D2 point charge, and C2 is the D0. Like in terms of
This I don't know.
R is a 0 point charge and C2 is a 4 point charge.
no, like R is a D4 because like it's a homology like in page 4. Like so like it's like it counts the rank of the ship on the surface. After like C1 is called the torsion, like which are like supported on some curves, so it's a D2 one charge, and like C2 like it's a torsion supported on points.
Ah, Pierre can translate.
Yeah,
between
so-
this is good.
Physical significance of the unit.
The story in terms of black hole evaporation. But in terms of electromagnetic charge, like this story that you
But they can be positive and negative, no?
yes, but like the rank, like the information is positive.
The rank, I guess, is positive, but then the other two may be negative. No?
Yes.
And so, inequality, we could still talk about inequality.
Yes, like because like it's the slope is it's C2 over R. So no, it's C1 over R. Like it's
Let's see.
Invocation. We give the quality, the fire. I will just, which one? Before the contractual. Variety factor to the funds. So, if we do little more here. This was the yeah. The intention to there will be two types, maybe by keeping surface and evidence surface. But in higher dimension, there are no classification. And for the classification, take of the comparing this type of RTB session for the so board or decomposition. Decomposition. After taking a high cover of the decline problem, we will decomposing that's the product from identity variety. I number to family variety to the classification of analytic type of mountain comparing this mountain attention. But so far, there are only four types of single analytic varieties are known up to the formation. First one, the function different values. The other one was called derived schema. The one for come back to can similarly to the individual point on the we should just consider the individual point on having a service, but it is not simply corrected for but it's fine to get the final get. And these two exceptional examples are taken from moduli sheet.
This BB, what does the BB stand for again? Wait, Bovell. So there's this classification of these things. up to some quotients and stuff, so that's why you can pass a simply connected. Because otherwise you can take a quotient by lattice or some finite group or something, and yeah, so this is part of the general classification of Kähler manifolds, and its hyperkähler ones are some of the most interesting. But this has been sort of a big project for decades, but no one has come up with new examples since O'Grady's. Right? Was that really 2010?
I know it's a nine. It's a nine.
Oh, right. Oh, right, yeah, the dimension, yeah, that was around 2000, I think it was like 25 years ago. Yeah, it was around 25 years ago that we had the last examples.
Yeah.
This is complex dimension, 6.
Yeah, yeah, complex dimension. Exactly.
And they are different from catering. Products.
Yeah. So these are all, so the classification is up to deformation. So you can have lots of things, I'm not sure about the O'Grady ones, the K3s, it's known as lots of deformations to this whole family of them, but strangely, they haven't found any examples which aren't in one of these families. So they might have thought, you would have thought there would be more.
So, yeah, okay, so how is it obtained?
Yeah. OG10 is okay. Effective result of single motion space. Not exactly. Solution of the or then we get to some single motion space. The biggest thing that goes. Yeah, some co-pattern. Then the crucial factor is that these are that there's no singularity, which is a symplectic manifold.
The local model was O'Grady 10. It's this Springer resolution of Lagrangian Grassmanni, or you can think of it as a quiver with a dimension 2 and 2 loops at the vertex. And then you can resolve it by blow up the singular locus. If you've heard about it, we've talked about these examples at some point in the past. Oh yeah, this is related to what Ricardo was doing, but Ricardo was doing a higher dimensional thing where you had to take a quotient by Z2. This is related, this is like, yeah. This was, you know, this Collette and Lane Zorger proved that those are the only ones that you could resolve of these singular moduli spaces. It's like the, yeah, so you take like a vertex with dimension 2 and 2 loops. And now you can't resolve, there's no parameters, you can't resolve it by variation of GIT quotient with no stability parameter. But if you blow up the singular locus, you get a resolution. And that's actually what you're getting is just the same as the Springer resolution of Lagrangian Grassmanni, because you can translate this quiver into an orthosymplectic one as well.
What you said is the 6th, right?
The
Dimension 6 is 2. The 6 is 2. What is the third?
Well, the 6th one comes from putting an SL2 at the vertex instead of GL2. You put GL2.
Well, mention 1.
They have the same singularity.
You put GL2 at the vertex, should give 10 dimension, complex dimension.
But like these methods are like positive, so you mean that you consider some like if you are just like locally near the singularity that you resolve, you use like this quiver.
Yeah, so the local singularity looks like this quiver, but if you take Lagrangian Grassmannian, that's exactly because maybe for Lagrangian Grassmannian, that's the 6th dimensional version, maybe I don't remember, but the quiver variety with GL gives you 10 dimensional. If you take a vertex with GL2, 2 loops. GL2, so you have 4-dimensional space of endomorphisms, and you have 4 arrows. You have 2 arrows and 2 reverse arrows. You have 16.
One of them is frequent. Since it's frequent, one of them is just frequent.
Yeah, exactly. Yeah. Yeah. So this is a product. Yeah. This 10-dimensional is a product of 6-dimensional with a 4-dimensional affine space locally. But I mean, this K3 is not globally a product. So the point is that you do 2 options. You can do the K3 and get this 10-dimensional thing, or you can do the abelian surface. In a abelian surface, you would have gotten a product if you tried to do 10-dimensional. So you can instead use SL2 and get a 6-dimensional.
Okay, so you did say by taking both of them SL2, but one with the trivial and the one without.
Right, exactly. But for K3, you have to have the 2 trivial because you're looking at moduli of G, it's natural to have the GL2, and then you don't get a global product, only locally, the singularity, you would get a product.
We will need to learn this.
But the reason why the relationship to Lagrange Gasman is what you explained about this equivalent orthosymplectic, there's this coincidence about SL2 and SO3 or whatever. It's called.
Yes, yes.
Okay, yeah, sorry.
So these are only examples where there are symplectic iterations. So basically all these examples are obtained from moduli space of C. So the interesting points are the examples from this is given the moduli space either shapes of the form of K to some. So but they say so there are no more examples which are obtained from the moduli space. But so we need another approach to obtain a new example. Here, can you think about the trying to examples by using this method? And in each time examples. Essentially, what the question was confined to the action. So we can encourage the kid to actually much more points because if we want the action of the transition with then this is the same as the symmetric product of habits. So and this is just simplification by the differential points. So this is one example. And I think also compared to other groups. Other example, interesting examples of doing about how to the like mindful model and group action. And they and she converted it by the generic group. So even if we start from a K-52 segment, we can convert another function type in just example. And more
A Abelian surface, G is a finite group.
and just give it fine, zero fine. And this means just means it is just a deformation type. Keep it
But doesn't that mean it's simply connected? It's in K32?
and this is simply corrected.
Right, so when we take quotient by G is a finite group.
But
How do we end up with this infinite?
now after taking the resolution, it becomes simply corrected.
K2 of A is simply connected.
Yeah, so the entity.
Ah, oh, I see. Just K2, right? A Kn of A is always simply connected. Oh, I see. Right.
Actually, this is not the Hilbert symbol for its step. This is just the function equivalent to the injection of form. So this just means the function type. But this is not the form.
Okay. And Sn, sorry, that's what is this Sn?
I need to get product of substance.
Product of surfaces. Okay. Product of surfaces. It looks like a sphere, Sn. Okay. S, the surface S to the nth power. Okay.
And much more by the work of the team people who know other they consider inform module and they that actually is some kind of finance quotient. Actually, they can go to a new example of new deformation type of English separate variety, but nevertheless they can give a new deformation type. So
Remind me, BGMM, it stands for
so the team.
Right, yeah, cool. Right, yeah.
Function types. So singular algebra. Here, singular varieties means that similar to the single case. This means that the regular part is simply connected. Is there some variation with definition of singular variety, singular variety? This doesn't normally talk about singular variety, singular IH variety, action that takes as only two factorial. Similar
Okay, and these new definition types is coming from which of these papers? The last one,
Actually,
Kawatani?
yeah, and they didn't give the smooth one, so no one.
They give you.
Some examples of predictive already gave some examples of singular varieties, and also in their recent work, they produce at least 9 unity function types of singularized variety up to junction 6.
So there's a lot. But there were lots of those, I guess. So 83 is a long time ago. It was before these O'Grady examples, anyway. But there must be a lot of singular examples, right?
There should be many more examples, but still it's not easy to construct examples. Actually, so they can only only produce examples up to dimension 6, and most of them in dimension 4. And actually,
So there's some finite list of deformation types. Well, finitely many families, I guess, if you include this parameter n, and we cannot find more even with the singular condition. Is that it?
it's not easy. So for singular multiplicity, they give in this group, infinite family of different unit function and devotion types of singular varieties.
So we have some infinite families,
Yeah. I think
but
here it's only infinite families.
they're the only infinite family. You think that there aren't any other infinite families, or you just don't know what
As far as as far as I know, yeah, there are
no other infinite families aside from these ones you have here, where you have parameters that you. So the moduli space for K3 and abelian surfaces, and aside from those, you don't know of any other infinite families. Even using these like different finite groups or something.
So actually, so here all of the simply connected ones are
Right.
also assuming the third constant.
Right.
So this notion comes from bilateral geometry, and basically this means that we take the best possible partial resolution.
Right. Yes, if you take a quotient by a finite group, right, then the regular locus will now have this non-trivial fundamental group with the G. So to resolve it, you take a cover, you get back to the original thing. So it doesn't produce a new example. You need to have something else. But in these examples of BGMM, they manage to get simply connected, even though the G can be finite there, right?
Yeah, actually,
So they take a resolution which makes it simply connected, or
yeah, that's actually the important thing is that to which you find the finite group for the fixed locus has codimension 2.
right, yeah, because then you can resolve, and that will get rid of this fundamental group. Yeah, right.
This is the extension.
But it's, if you take like if you take the Duval singularity or Kleinian singularity, you have fundamental group on the complement of origin. But when you resolve it, there's no fundamental group anymore for the resolution of singularity or the deformation. So then this happens whenever you have quotients by finite group acting symplectically, and the fixed locus is codimension 2. You can resolve this codimension 2 singularities of Duval singularities, and if you're lucky, then the result is this property of the regular locus being simply connected. That does work in some of these examples. But you want to do something else, a different technique, using this duality, right?
And then it's easy to produce a new example, even if they are similarity.
Yeah.
So these are they consider the quotients of the type generate mathematics. Actually, we can't. It is known that we can't consider a similar construction for OG10 and OG6.
So I don't know if this is a big thing in physics, but in mathematics, this is one of the problems which has, I think, inspired a lot of activity over the last few decades to try to find new examples of these IHS, right? It's a new compact hyperkähler manifolds, or now I guess they're allowing also singular ones because they didn't manage to find any new smooth ones.
There were recent papers.
Yeah, but they don't ever, they construct sometimes new example, but they're always deformation equivalent to the ones that they have. But what the if you allow singular, then they can construct sometimes ones that are not deformation equivalent.
Yeah, so there is a problem of modular spaces for instant ones on either P4 or P3.
Hmm.
And there is a question about how this modular space looks like. We don't have the same. So
Mhm.
there is a continuous information to one to another. Or no, right? So typically when we look at quibbles, we look at
Mhm.
modular spaces on line singularities.
Mhm.
Or we see too.
Right.
But some physicists are looking at the compact problem.
Right. So if you look at the compact problem here, then I guess the answer is if you look at the abelian surface of the K3, you cannot construct any smooth examples that way. You have to do something more than, yeah, you can't do any which are not definition equivalent. This is known since I guess Khaled and Lane Zorger basically, but you can try to do more sophisticated things like these quotients and stuff. But they don't work to construct new smooth examples at the moment, only singular ones. Right? Is this the good summary?
So, so this is the summary of the. So the aim of this talk is to find example by containing unsquashable singular by different singular variable. So more and think about that's
So maybe you can try to state the results and then we can go get lunch and then we have still until 1 o'clock in here.
oh
And afterwards we can move somewhere else and discuss. So let's try to take a lunch break soon. Yeah, but state your results.
yeah, the first one about the duality of the involution. We assume the current is from the other the surface gene and so there are the shift is later on. I think that we are using they're not in here, very simple. But okay. So we can just start with this. Thinking that the function value is the function value. And for our next one,
Ah.
and that is not about this.
It was only birational, but now you say in some case it actually extends
Yeah.
If it only- to biregulated. All right. Now you're gonna take the quotient by this, right?
Okay. We need to give additional values. But
Ah. Okay,
so when I said earlier, so the musical part, that there's nothing really even by taking the gel sheet. And even if these conditions are not strong on the other way, even if this is not regular, the homogeneous field. On the boundary, on the complement of the music part, the image of a sheaf and the inversion is not given by the gel sheet. Which is
and so the dual is not actually gonna be Giesecke semi-stable or something. It doesn't preserve the property of being Giesecke semi-stable.
actually for sheaves on the complement of the musical part, the physical instability never preserves.
Never preserved, yeah, that's what I'm saying. So you couldn't possibly define it by dual, it wouldn't be in the locus. You have to define it in a different way.
Actually, we don't know the exact image of a sheaf and the inversion. So we know that if these conditions are satisfied, then the automatic step
Right,
to a regular map, but it's not easy to identify the precise image of a sheaf.
okay,
And the,
so it's hard to write down the formula, you say. But it couldn't be a dual because it wouldn't be Giesecke semi-stable.
yeah,
Okay,
this is the problem.
fine.
Assume was that. That your team, inversion of the regular is what is this? So now the actually on the model we can talk the portion for this information. This course this possibility to have all the partial relation with this. Think about it. But these are only finally missing reference. So they are only actually single. And finally, there is a problem. of this. So actually, in the part.
Okay, so the theorem is that it admits a symplectic partial resolution, which has Q factorial singularities, finitely many singular points, and the simply connected regular locus. This is for 306. And D, sorry, what was D again?
D is the involution.
Oh, the involution, the involution. This is this related to this example of Ricardo Carini, who was studying this genus 3 involution around a genus 3 curve in a moduli space of K3, but maybe it was for the group SL2, I think.
Do we consider compact model?
Yeah, for K3, so
Okay.
compact, but he didn't manage to get so far as to construct the resolution, the global resolution. I think he was looking at the local. Okay, so maybe it's related, but I'm not sure. But this is 306. This means it's rank 3, rank 3.
The smallest example.
Mm-hmm.
Rank 204 is the same as only 10. For rank 206, this is
This is rank 3, so the local model would be a vertex, a dimension 3, and some right. Right.
Yeah.
And if you take quotients by this Z2, then you can take a partial resolution. It's still going to be singular. It'll have some Q factorial terminal singularity. Is this a singularity we know? Do we recognize what the singularity is? Quotient of what is it, sir? You take a partial resolution after you take quotient.
But outside of the very singular point, there are other fixed points by the evolution.
Okay, well, we'll discuss it after the break. Other questions?
You have really a finite set of singular points, so they are just like either.
Yeah.
Identify the singular point of the model.
But you're going to explain to us what these isolated singularities look like then, basically, after the break.
It's a bit the singularity comes from fixed point on the smooth part of the model space.
Ah, so it doesn't come from the singular locus of so that part gets resolved, but
Yes.
so then these are understandably, these are like orbifold singularity, like finite quotient singularity.
Finite quotient, so
It's a Z2 quotient singularity, all of them, I see, but Z2 quotient singularity where the codimension of the fixed locus is greater than 2, so you can't resolve.
yeah, okay, indicate
So some C2K divided by Z2 singularities then. That you're saying for some K.
Minimal C,
Hmm?
minimal CL.
Yeah, for some N, yeah, I guess you didn't tell us what the dimension of the singularities are, but or the codimension. Oh, all right,
Yeah,
this top
fine.
codimension, right? So it says 20 dimensional, so it's so it's C20 divided by, yes, that's whatever.
See that.
Yeah, exactly. C10 singularities. Perfect. Okay, well, let's thank Rio then. Any other questions? So we'll go get lunch and then we'll have a little bit more time until 1 here.